You've probably heard the word process used in your plant. What does the term process mean to you? To many people, a process is all of the piping, valves, and other equipment that goes together to make up a plant system. For example, equipment like this shell and tube heat exchanger would be considered part of a process. Actually, the process is what's going on inside the heat exchanger, not the heat exchanger itself. The heat exchanger simply facilitates the process. This particular heat exchanger cools a fluid. The process, in this case, is the cooling that takes place. Of course, this is only one example of a process. Most processes can be thought of as a sequence of changes, such as changes in temperature, flow, level, pressure, even the chemical makeup of a substance. And most process changes involve the transfer of energy. The term process can be defined in several ways. For our purposes, we'll define a process as any physical or chemical change of matter or conversion of energy. That means that the mixing of two or more substances, such as the fluids in this tank, is a process. And the burning of fuel to supply heat for making steam in a boiler or to heat another substance in a fired heater is a process. The transportation or movement of a product, accomplished by a material handling system like this one, is a process. The definition of a process includes many changes that cannot be seen, such as the conversion of sunlight to heat that takes place in this solar panel. These four examples are only a few of the many processes that are found in modern industrial plants. In each of these examples, and in all other processes, matter is physically or chemically changed, or energy is converted. Since many of the changes that occur in a process can't be directly observed, various types of instrumentation are used to monitor process parameters. Instrumentation systems take the monitored information and use it as an input in order to control the operation of system components and maintain the process within proper limits. In most cases, process parameters are referred to as process variables. Of course, specific process variables change from one system or process to another. Four of the more commonly seen variables are temperature, pressure, level, and flow. As you continue your studies of instrumentation and control systems, and as you learn about the processes in your facility, you'll discover many other process variables as well. Inside this shell and tube heat exchanger, steam is used to heat another fluid. In this case, the steam, which supplies the heat energy for the process, is called the working fluid. A working fluid is the fluid that performs the function of a process. System piping allows steam to enter the heat exchanger here. It then flows through the shell or outer housing. In the heat exchanger shell, the steam gives up its heat to increase the temperature of the second fluid, which flows through the tubes. The fluid to be heated by the process enters the heat exchanger here and passes through the tubes. After being heated in the tubes, it flows out of the heat exchanger. In this example, the temperature of the hot fluid leaving the heat exchanger is measured by a sensor. The control system controls the temperature by positioning this valve, which regulates the flow of the working fluid leaving the heat exchanger. Process systems can be categorized as either closed or open systems, depending on how the working fluid flows through them. This can be considered a closed system. That means that the working fluid never leaves the system. The working fluid, steam, flows into the shell and gives up its heat. This causes it to condense back into water. The water, or condensate, then flows out of the heat exchanger and is returned to the boiler to be heated and converted to steam again. In open systems, the working fluid leaves the system. The process that takes place in a boiler or fired heater is an example of an open system. In fired systems, fuel is mixed with air and burned in a furnace. The hot gases that result from the combustion of fuel and air are the working fluid. They supply the heat that's used in the process. After supplying heat in the furnace, the combustion gases pass through the furnace and up the stack, leaving the system. So this is an example of an open system. You'll find more information on the topics we've discussed in your workbook, together with some additional examples of typical processes. The workbook also contains questions to let you check your understanding of process and system characteristics. As we saw in the last segment, most processes involve the transfer of energy. But what is energy? Energy is defined as the capacity of a material to do work. As you can imagine, in modern industrial plants, energy takes several forms. For example, many machines and system components are driven by motors. Electrical energy is used to power these motors. And, like in your home, industrial facilities make use of electrical energy to power area lighting systems. The sophisticated instrumentation and control systems found in many industrial plants are frequently powered by electrical energy as well. Boilers and fired heaters make use of the chemical energy in fuel. This chemical energy is converted to heat by the combustion process. In a boiler, the heat energy is then used to convert water into steam. In a fired heater, the heat is used to increase the temperature of another fluid. In fluid process systems such as these, the reason the working fluids are able to perform work is that they contain energy, in this case heat. The energy they contain is transferred from one form to another, from one fluid to another, or from one place to another during the operation of the system. There are three categories of energy: potential energy, which is energy of position; kinetic energy, which is energy of motion; and internal energy. Internal energy is the energy of molecular motion within a substance. The fluid in this elevated rooftop tank has no motion, but it contains potential energy because of the tank's height or position. The energy was transferred into the fluid when it was pumped up into the tank. If a piping path is provided, the fluid will flow out of the tank, and as it flows, it will perform work. When flow occurs, the stored potential energy in the fluid is converted to kinetic energy, or energy of motion, and work is performed. The amount of potential energy a fluid contains is determined by two factors: the fluid's height and its mass. Here we see two tanks. Each tank contains the same amount of exactly the same fluid. Does the fluid in each tank have the same amount of potential energy? No, they don't. The tank on the right is positioned higher. This means more energy was transferred into the fluid in order to get it into the tank. Therefore, the fluid in the right tank contains greater potential energy than the fluid in the left tank. Here again, we see two tanks, and both tanks contain exactly the same fluid. In this case, however, both tanks are at the same elevation. But notice that the left tank has a higher level than the right tank. This means that more work was performed and therefore more energy was transferred to get the fluid into the left tank than the right tank. So the fluid in the left tank contains more potential energy than the fluid in the right tank. We said that the potential energy contained in a fluid also depends on the fluid's mass. Mass is defined as the quantity of matter in a body as measured in its relation to inertia. The mass of a given body is determined by dividing its weight by the acceleration due to gravity. Weight or heaviness is a characteristic of all things. Weight is a measurement of the attraction of a material body by the gravitational pull toward the center of the earth. This illustration shows two tanks containing two different fluids. Each tank contains the same amount of fluid or has the same level, and the two tanks are at the same elevation. The fluid in the right tank is heavier than the fluid in the left tank, or has greater mass. This means more work was required to get the fluid into the tank, so more energy was transferred. Therefore, the fluid in the right tank contains more potential energy than the fluid in the left tank. In addition to height and mass, another factor which influences the potential energy of some process fluids is pressure. This air compressor, for example, increases the pressure of air and pumps it into the tank behind this piping, called an air receiver. Like pumping a fluid to a higher elevation, increasing a fluid's pressure requires the addition of energy to the fluid. The potential energy contained in the pressurized air stored in the air receiver may then be used to perform work, such as the operation of control valve actuators and other instrumentation and control devices. The potential energy in a pressurized fluid reflects how much work was involved to increase its pressure. Since the fluid's pressure is determined by the amount of work needed or the amount of energy transferred, pressure is an indication of the amount of potential energy a fluid contains. The higher a fluid's pressure, the more potential energy it contains. When a pressurized fluid is allowed to flow, the potential energy contained in the fluid is converted to kinetic energy, or energy of motion. In the process, work is performed. This electric generator, for example, is driven by a turbine. The turbine uses the flow of steam as its source of energy, converting the kinetic energy in the steam to mechanical work to turn the generator. A fluid's kinetic energy is determined by its speed of motion or velocity, and also by its mass. The faster a fluid moves, and the greater its mass, the greater its kinetic energy, and therefore the more work it is capable of. The third energy category is internal energy. The amount of internal energy a fluid contains is determined by the activity level of the fluid's molecules. The movement of molecules within a fluid or any other substance increases as heat is added. So the more heat a fluid contains, the greater its internal energy. Temperature is frequently used as a measure of a fluid's internal energy. You'll learn more about temperature and internal energy in the next segment. There are questions in your workbook that you can use to test your understanding of the types of energy found in fluid processes.
Also in the news, this from the National Weather Service. The area's hot spell continues. Yes, be prepared because we're expecting another real scorcher today, folks. The temperature this afternoon is expected to reach 97 degrees Fahrenheit. That's 36 degrees Celsius. So if you can, stay home in front of your air conditioner where it's cool. But wherever you are, keep your radio tuned right where it is, where you'll hear all your favorite music from
We're all accustomed to the term temperature. We use temperature every day to describe how hot or cold the weather is. Temperature values are also used to describe how hot or cold a process fluid is. So before we discuss heat and heat transfer, we first need to talk about the measurement of temperature in industrial processes. Temperature is frequently, but not always, a measure of the amount of heat a substance contains. There are 4 temperature scales which can be used in industrial instrumentation and control systems: Fahrenheit, Celsius, Rankine, and Kelvin. You may already be familiar with the Fahrenheit and Celsius scales. These are the 2 most commonly used temperature scales. We'll use the boiling and freezing temperatures of water to compare these temperature scales. The Fahrenheit scale is used in many systems. On this scale, water boils at 212 degrees, and water freezes at 32 degrees. In other instrumentation and control systems, the Celsius temperature scale is used. On the Celsius scale, water boils at 100 degrees and freezes at 0 degrees. While working on the instrumentation systems in your plant, you may have to convert temperature values measured using one of these scales to their equivalent values on the other scale.
Hey, Paul. I'm trying to check the temperature loop in the boiler feed water preheater.
Yeah.
But its display is in degrees Fahrenheit, and our instruments read degrees Celsius.
That's no problem. I can show you how to convert from one to the other. On the Fahrenheit scale, we know that water boils at 212 degrees and freezes at 32 degrees. That's a difference of 180 degrees. On the Celsius scale, water boils at 100 degrees and freezes at 0 degrees. That's a difference of 100 degrees. So 1 Celsius degree equals 5/9 of a Fahrenheit degree. The formula for converting Fahrenheit to Celsius is Celsius temperature equals 5/9 times the quantity Fahrenheit temperature minus 32. To go the other way, it's Fahrenheit temperature equals 9/5 times the Celsius temperature plus 32.
Now, why is 32 a factor in both formulas?
Both formulas use the freezing point of water as a baseline. That's to account for the 32-degree difference in the scales.
I see. Okay.
Well, try out the formulas with the freezing and boiling point of water. You'll see that they work.
Great. I will. Thanks a lot.
My pleasure.
2 other temperature scales you may see are the Rankine and Kelvin scales. These 2 are less common in industrial applications than Fahrenheit and Celsius, but they are sometimes used, especially in processes that operate at extremely low temperatures. Both the Rankine and Kelvin scales are based on the concept of absolute zero. Absolute zero is the theoretical point where all molecular activity stops. You'll find additional information on the Rankine and Kelvin scales in your workbook. It also contains formulas for converting between all four of these temperature scales, together with a table which compares temperature values in the four systems. When two substances or bodies at different temperatures are in contact with one another, energy flows from the hotter one to the cooler one. The energy that flows from one body or substance to another because of a difference in temperature is called thermal energy or heat. The flow of thermal or heat energy from one substance to another is called heat transfer. Heat transfer, such as that occurring in this cooling tower, may be a part of many fluid processes. For example, heat is transferred in boilers, which use the heat from flame and combustion gases to generate steam. Heat exchangers like this one are used to cool process fluids. In this case, a cooling fluid absorbs heat from the process fluid as they flow through separate paths in the heat exchanger. Other heat exchangers are used to increase the temperature of process fluids. In these cases, a hot working fluid, such as steam or hot water, gives up heat, which is transferred to the process fluid. No matter what type of process or system is involved, heat is transferred in one or more of three ways: by conduction, convection, or radiation. Conduction is defined as the flow of heat through or across a solid conducting surface. One example of conduction is the heat transfer that occurs through the walls of the tubes in a boiler. In this boiler tube, heat from the flame or combustion gases flows through the tube walls by conduction. Convection is the transfer of heat by circulation of a fluid that contains heat. In this boiler, for example, heat is transferred from the furnace to the superheat section by circulation of the hot gases from one area to the other. Convection may be forced using fans, pumps, or other devices to cause the fluid to flow. With natural convection, fluids circulate and mix naturally because of temperature difference. Radiation is the transfer of heat by waves of energy that behave similar to light waves. In the boiler furnace, some of the heat transfer from the flame to the furnace tubes is by radiation. No material medium is needed for radiation heat transfer. Radiation heat transfer can only occur when there is a direct, unobstructed line of sight between the substance radiating the heat and the substance to which it is being transferred. When an inspection door in a furnace is opened, gas, in this case outside air, flows through the open door into the furnace. In spite of the airflow inward, heat flows out. With the door open, you can feel the heat. What you feel as heat is a temperature increase sensed by your body caused by radiation heat transfer. In most plant systems and process operation, the heat transfer that occurs is a combination of conduction and convection. Conduction occurs across solid surfaces such as metal tubes and vessel walls, while convection takes place when fluids are circulated by pumps and fans, or when temperature differences cause natural circulation. Since it behaves similar to light, radiation heat transfer is commonly observed in boilers, fired heaters, or other industrial equipment which makes use of flame as a source of heat. In these components, heat transfer occurs as a result of all three methods: conduction, convection, and radiation.
You know, some people use the words temperature and heat to mean the same thing, and sometimes they do, but in some cases, the two words are totally unrelated.
I'm not sure I follow you. Don't we use temperature instruments to monitor and control heat?
That's right, but temperature alone isn't always a good indication of a fluid's heat content. Now, our boiler is a good example. Now, we monitor temperature inside the steam drum. But to see why temperature isn't a reliable indication of heat, you have to understand what's happening inside the boiler.
In a boiler, fuel is mixed with air and burned. The heat which results from the combustion process is transferred to water in order to boil it, to produce steam. In a typical boiler, feed water is pumped into the steam drum at the top of the boiler. From the steam drum, It flows down through the downcomers and into the bottom drum, sometimes called the mud drum. It then flows from the bottom drum up through the furnace risers and back to the steam drum again. When the boiler is fired, heat is transferred to the water in the risers by all three heat transfer methods: by radiation from the flame to the tube walls, by conduction through the tube walls, and by convection due to circulation of the hot gases in the furnace, as well as circulation of the water in the tubes. This heat transfer causes the temperature of the water to increase. This heat, which results in a temperature increase, is called sensible heat. Sensible because the results of the heat transfer can be sensed. In this case, a change in water temperature is sensed. As the water temperature continues to increase, it reaches the boiling point. Then, as additional heat is applied, it begins to change from a liquid to a vapor. Now, what flows into the steam drum from the risers is a mixture of steam and water. The conversion of a substance from one form to another by the transfer of heat is called a phase change. The boiling of water is one example of a phase change. A substantial amount of heat is required to change water from a liquid to a vapor. And although the heat is transferred to the fluid to cause the phase change, the temperature of the fluid does not increase. This is because the heat energy is being used to change the water into steam, rather than to increase its temperature. The heat required to cause a phase change is called latent heat. In our example of a boiler, it is referred to as the latent heat of vaporization. In the steam drum of a boiler, the water exists in two states, both liquid and vapor, and both the liquid and vapor have the same temperature. But the vapor, or steam, contains much more heat than the liquid. This is because the steam contains not only sensible heat, but also the latent heat which was transferred to it to cause the phase change from liquid to vapor. The temperature at which a fluid can exist as both a liquid and a vapor is called saturation temperature. This is also the temperature at which boiling of the fluid will occur. The saturation temperature for a fluid varies with pressure. As pressure increases, saturation temperature increases. So, to know whether or not saturation conditions exist in a process, you have to know both the temperature and the pressure of the process fluid. In some boiler systems, steam at saturation temperature, referred to as saturated steam, is used for process purposes right off the top of the steam drum. In other boiler systems, like this one, steam flows from the steam drum through another set of tubes called a superheater. In the superheater, heat from the hot gases passing over the tubes is transferred to the steam flowing through them by a combination of convection and conduction. Since the steam is no longer in the presence of water, this additional heat increases the steam's temperature to greater than saturation temperature. Since this heat transfer causes a temperature change, it's sensible heat, not latent heat. Steam that is at a temperature higher than the saturation temperature for the existing pressure is called superheated steam. Steam can only be superheated when there is no water present.
So you can see that a boiler is a good example of how temperature doesn't always reflect the amount of heat that a fluid contains.
Wow, I'd heard the terms sensible and latent heat before, but I'd never heard the difference between them explained. How does our system allow for latent heat?
Well, let's take a look at the instrumentation drawings. That way you'll be able to see how the control system works.
Great.
Your workbook has an illustration called a temperature enthalpy curve, which shows the relationships between sensible heat, latent heat, temperature, and the phases in which water can exist. And it has some review questions which will allow you to check your knowledge of this information. You'll find that a thorough knowledge of process characteristics and the concepts of energy, temperature, heat, and heat transfer will help you better understand not only the processes we have seen, but other processes in your facility as well. Remember, however, that designs and operating principles differ. So always follow the manufacturer's instructions and your facility's guidelines before working on any process system.